Okay, so we have a lot of things now that will give us pH. And we are used to now, or hopefully getting used to the fact that acids have a pH and bases have a pH. And hopefully that we are starting to get used to the fact that, hey, I can recognize HCl as an acid, or H2Cl3, that's an acid, or NaOH, that's a base, or MgOH2, that's a base. Okay? But here's what happens. Okay? In the chemistry world, nothing can be simple. So what happens is, can something like sodium carbonate be an acid or a base? Or could it be neutral? Because if you look at the formula of sodium carbonate, the formula is just NaCO3. But if you put sodium carbonate, I'm sorry, it should be Na2Cl3. If you put sodium carbonate into water, okay, even though it doesn't look like an acid or look like a base, this compound actually falls into the basic range, and it has properties of bases. So what is it about this that would make it act like a base? Okay, so one of the things that we have to look at is what actually happens when you add an acid and a base together. And when you take an acid and a base together and add them together, you always get water, but you always get a salt as well. So what happens is salts have a relationship to acids and bases. So because of that relationship, salts can affect the pH of a solution. But not all of them do. So there's lots of things that this is going to depend on, and we have lots of little rules for if this happens, then you'll have an acid. If this happens, then you'll have a base. So there's always lots of little rules. Okay, so we're going to start with something like NaCl and KNO3. Okay, and we're going to look at the fact that will these affect the acidity of a solution? And NaCl is normal table salt, and we use it all the time. And your answer to this should probably be that these do not affect pH. Okay? So they are salts, but then why don't they affect pH? Well, there's a reason. And that reason has to do with where the ions come from. Okay? And we have cations and anions, and you do need to remember those terms. Okay? Your cations are positive charge, and your anions are negative charges. And when you split this up, you get positive and negative charges. Okay? And so it depends on where the ions come from, and we're going to start with the negative charges first. Okay? And if I look at Cl and NO3, these are conjugates of strong acids. Okay? And the acids that they're conjugates of are HCl and NO3. So if I have HCl, its conjugate base is Cl minus. If I have HNO3, its conjugate base is NO3 minus. And because they are conjugates of that, the Cl minus and NO3 have no attraction for hydrogen. They don't want anything to do with that H plus. And part of the reason is what these do, and it's easiest to see with Cl. If you look at the dot structure of chlorine, okay, chlorine is literally short one electron. So if it takes hydrogens, okay, one electron, and it steals it, okay, then that chlorine has its 8 electrons around it, and it has its -1 charge, and it's essentially very happy. Okay, whereas the hydrogen over here is now a +1 charge, and this chlorine, now that it's happy, really doesn't care about that hydrogen anymore. Now, this hydrogen does need to go someplace, okay? We can't have that hydrogen just floating around in water, but the chlorine doesn't want it anymore. So that hydrogen will glob onto another water molecule. And there is our acid molecule, okay? And basically NO3 is doing the same thing, okay? So how about this compound, Na2SO4? Would this affect pH? And what you essentially need to do is you need to take these compounds and you need to split them apart, okay? And when you split them apart, I have Na plus ions and I have, SO4 minus ions, okay? And when I look at the second part of this, the SO4, that is a conjugate of a strong acid, okay? The strong acid being Na2SO4, okay? So that conjugate's basically going to have the same issues. This sulfate is going to have the same issues as that chlorine. It doesn't want any hydrogens. It could care less about hydrogens, so it's not going to attract any, okay? So as you just keep going down here and looking at other examples, and I'm only looking at the negative ions right now. If I break this apart, I have Sr2 plus, but I have the Br minus. Is that a conjugate of a strong acid? And the answer is yes. Oh my goodness. That's going to be HBr. Okay? So, apparently, if the negative ion is from a strong acid, then it has no attraction for hydrogen. Okay? But what about the positive ions? Okay? Wouldn't they affect pH? So if you look at sodium and potassium, okay, would they have an ability? And the answer to that is no. They are not going to affect pH, and essentially almost for the same reasons. These are conjugates of strong bases. Okay, and so what are the strong bases? Well, NaOH is the strong base, and KOH is the strong base. So essentially then, these sodium ions and potassium ions have no affinity to attract a hydrogen, but would also make sense that they wouldn't attract a hydrogen because both of these are positively charged, correct? So they would have no reason to attract a positively charged hydrogen. In fact, they would repel it. Okay? If this hydrogen came up close to this, they don't have any reason to be together, so they would just be repelled apart. Okay? So, basically, positive ions have absolutely no reason to attract a hydrogen. So the rule then comes down to this. Okay? And this is rule number 1. Ions, anions, or cations that come from strong acids or strong bases will not affect pH. So, there's our first rule, and then there's a lot of salts that this applies to. Okay? So, if I have the salt SRI2, all you gotta do is break this apart, and you break it apart and you come up with, oh, I have Sr2 plus ions, and I have I1 minus ions. Okay? First of all, going back to the fact that this is going to have no reason to attract a hydrogen. Okay, so that's pretty blatant right there that that's not going to form an acid. But this could attract a hydrogen, but it's a conjugate of a strong acid, which would be HI, so it's not going to affect pH. Okay, so there's your first rule. So you have to know what your strong acids and your strong bases are. So then, what salts will produce a solution that's acidic or basic? And we're going to start with salts that produce basic solutions. Okay, and our first salt that actually will produce a basic solution is going to be NaF. Okay, now, if you take NaF, first of all, and you break it apart, you get Na plus ions and F minus ions. And we've already discussed the fact that there's no reason for that to attract a hydrogen. So what would it be about the fluoride ion that would attract a hydrogen? Well, it turns out that fluoride comes from a weak acid. Okay? And what happens then is, because it's from a weak acid, it actually would want to steal a hydrogen from water. Okay? Because essentially, it would rather be in the HF form. Okay? It would rather be HF than F minus. So it's going to take a hydrogen from the water molecule. Well, when it does that, what it leaves you with is OH minus. Okay? This water changed to an OH minus. Well, that's a base. Okay? So F minus is essentially a conjugate of a weak acid. Okay, and I already talked about which. So it does not have the ability, so it does have the ability to attract hydrogen from a weaker party. Okay, and that's water. So then we just have to look at these compounds in general and say, okay, what about KCN? So I look at KCN, break it apart. K plus, Cn minus ions. K plus, same reason as always. Okay, it's a positive ion, it's not going to attract hydrogen. But what about Cn minus? Okay, and here's where, we just need a little bit more experience, but HCN is a weak acid. Okay, so you just have to say, okay, can I put a hydrogen on this and have it become an acid? And pretty much everything you can add a hydrogen to it and it will become a weak acid. Well, where is the only possible place it could get a hydrogen from? The only possible place it could get a hydrogen from is a water molecule. Okay? So that will become HCN plus OH minus. There is your base again. Okay? So that's why it's producing a basic solution. And it doesn't matter what the substance is. Okay? So we can do this again with sodium acetate. Cut it in half. Na plus. Don't care about. But what about C2H3O2 minus? Can that be an acid if I put a hydrogen in front of it? And if I put that hydrogen in front of it, it becomes acetic acid. So the C2H3O2, the acetate ion, where is the only place it could steal a hydrogen from? And the only place it can steal a hydrogen from is from a water molecule. So essentially this compound right here, they have a stronger attraction for the hydrogen than the oxygen in it does. So it basically rips off a hydrogen and becomes HC2H3O2 plus OH minus. So we're a basic solution. And we can continue this with another one, but I'm just going to give us the rule here. And here is the rule. This should be up here. Any salt with a cation from a strong base, but the anion is a conjugate of a weak acid, will produce a basic solution. Okay? So the cation, being the positive one, is from a strong base. That way we can ignore it. Okay? And what you have to do is look at the negative ion, and if that's the conjugate of a weak acid, it's going to produce a basic solution. So, one more example here. I have strontium carbonate. Okay? Strontium, 2 plus ion. Okay? It's also a conjugate of a strong base, which would be SrOH2. But it's also a 2 plus ion, so it's not going to attract a hydrogen. But then you have the CO3 2 minus. So if I have this CO3 2 minus, is that a conjugate of a weak acid? And if you put H2CO3 in front of this, then you have carbonic acid. So yes, it is a conjugate of a weak acid. So the only place that this can obtain a hydrogen is from water. And so what you are going to get is HCO3 1 minus plus OH minus. So we have a basic solution. Okay, so then the next one is going to be salts that produce acidic solutions. And these are fewer in between. You actually have a lot more salts that produce basic solutions than you do acidic. Okay, so here we have ammonium chloride, and we're going to do the exact same thing that we've done before. We're going to break this apart. Okay, and when I break it apart, I'm going to get ammonium, and I'm going to get chloride. Now, chloride is the conjugate of a strong acid, HCl. So because it's the conjugate of a strong acid, we get to ignore it right away. But ammonium is not a conjugate of a strong acid, nor is it a conjugate of a strong base. So what happens with this ammonium is when you put it into water, it actually has the ability to give up a hydrogen to the water, and now you're going to get NH3 plus H3O plus acid. That is our acid molecule. Okay? Now, I don't have a lot of these for examples, so this is essentially the definition. Any salt that has a cation that is a conjugate of a weak base, and the anion is from a strong acid, will produce an acidic solution. Now, weird salts. Okay, there is something called hydrated salts. Okay, and so there are a lot of salts that when you put them into water, okay, the metal ion is going to become surrounded with water molecules. Now, if I take this AlCl3 and break it apart, okay, we can get rid of the chlorine because of all the same rules that we had before. But what happens is this aluminum that has a 3+ charge now does something really weird, okay? And what happens is, the weird thing that happens is this right here. It literally gets surrounded by water molecules, okay? This is called a complex ion, and it has something in it called coordinate covalent bonds. Two things that we need to talk about. But it's a complex ion simply because it has all of these water molecules around it. Okay, that's what makes it a complex ion. Okay, so essentially what this compound is, this compound here, is actually now aluminum with water molecules around it, and there happens to be 6 water molecules around it, and it happens to have a 3+ charge. Okay? Now, there are a lot of molecules that do this, and they have really weird names. So I'm just going to jump ahead before I come back and talk about why this would be an acid or a base. Okay, so not all metal ions will do this, but there are a select few that do. And if you look at your Ka chart, okay, there is a list, or these are among the list in that Ka chart. And they have really weird names. Okay, and they all start with hexa aqua. Okay, and basically the hexa is 6. The aqua is referring to the water that surrounds it. So basically 6 waters, so metal ions surrounded by water molecules. And then the last thing is what metal ion it is. So this is hexaaqua iron 3. Then you have hexaaqua aluminum, hexaaqua copper, hexaaqua lead, hexaaqua cobalt, hexaaqua iron 2, and hexaaqua nickel. Okay, these happen to be the ones that are on your list. Okay, and they all would look something like this. Okay, they're nothing really special except their formulas are weird. Okay, so this is hexaaqua iron with a +3 charge, and it has all those water molecules around it. This is hexaaqua copper, and it has all those water molecules around it. But because it has all those water molecules around it, these actually have the ability to donate hydrogens. Okay, so if I go back to this hexaaqua aluminum, okay, and this gets a little bit muddled because there's a lot of water molecules around, because you're talking about the water molecules that are part of this, and then you are also adding them to water, so there's actually even more water molecules around. So there was water molecules everywhere in this. But what happens is one of these H2Os, one of the 6, and it doesn't really matter which 6 because we never really know, will actually give up a hydrogen to the H2O. And so when it does that, you get the H3O plus, but then this becomes weird because now you still have aluminum and you still have water, okay? But one of the waters broke apart. So now you only have 5 waters. But that one water that broke apart, okay, was an so it was an HOH, okay? We gave up one of the hydrogens, so one of the hydrogens went to this. So I still have this OH left that's tacked onto this compound. So the other product is AlH2O5 OH minus. I'm sorry, OH plus 2. It's not OH minus, it's OH plus 2. Okay, we went from a plus 3 to a plus 2. This is the weird part. That makes, this makes this solution acidic. So these weird things, whenever you see these in a solution, essentially all of these will give you acidic solutions. Okay? And this is the equation that they all tend to look like. Now, if you look on the Ka sheet, you will see this listed as the Ka, and then this listed as the Kb, so you can compare them. All right, one last issue. What happens if both are conjugates of weak acids and weak bases? If this is the case, then you have to write two equations, because if I break this in part, I'm going to get NH4 plus, and that's a conjugate of a weak base, and I'm going to get C2H3O2 minus, and that's the conjugate of a weak acid. So this will react with water, and this would produce an acidic solution. And this would react with water, and it would produce a basic solution. So, is the solution acidic or basic? Well, the only way you can find out is you have to look at the Ka and the Kb. And whichever is larger, that would take precedence over the other and would be the stronger. So if the Ka were bigger than the Kb, then you would be acidic. If the Kb were bigger than the Ka, then you would be basic. I just happened to choose one where the Ka and the Kb were the same. And so if that ever happens, then you're neutral. Okay? So, a lot of information there about salts. And hopefully we can try the worksheet.